I'm assuming everyone on this channel knows about microcontrollers and programming. A device that we as a programmer program it to whatever we want it to do. It is separated from our computers because you can implement those devices into your electronics. And I think one day every programmer asked themselves, what's going on inside this chip? Those who know such a question will not be answered on their own, will start searching and encounter something called logic gates. Logic circuits are bottom of the iceberg of computing in general. All programming languages' purpose is to help us direct those circuits. It is like a biology of computer science. We come across logic gates a lot of places, especially in video games, like Minecraft. As we know, Redstone is basically a tool to make logic circuits in Minecraft. I'm one of those programmers who asked that question too. And when I started to learn it, computers become having a different point of view in my mind. Then I come across with the Beniter's YouTube channel, and I immediately want to build my own 8-bit computer too. You can make logic circuits in various ways. You can use simulation programs, or various video games, or even in real electronics, with using TTL logic chips and transistors. I want to make connections between real electronics and logic simulator softwares, like FPGAs, but much simpler and more accessible. This idea of simulating logic circuits is born with this program, called Bitmap Logic Simulator. This particular simulation was published on 2015 on September 2 by Realhead. Once you open the program, it wants you to open an image, and program starts to process this image by some rules. Rules are simple, and there are only 3 rules you need to know before you build circuits. 1. If there are light-colored pixels, then they are going to have 2 states, 1 or 0. That indicates they are wires and conduct signals. 2. If there's a shape like a triangle in 3x3 space, then it will act as a NOT gate, and the endpoint of it will change states when the body of this shape changes state. And 3. If you want to cross 2 wires and don't want to intersect each other, then you have to put a black pixel in the middle of the crossing. You need to recreate all the components that you need in your logic circuits to use it. It doesn't have a floating state, so you can connect 2 NOT gates and like this. That way you can have a NAND gate. If you want to make a diode, then invert the signal 2 times. And if you connect 2 or more diodes outputs together, you will have OR gate. You can create with those parts all logic gates, latches and flip-flops, multiplexers and decoders, etc. This restricted place suddenly pulls me in because I have so much creative control and limited space to solve realistic problems. There are many more programs like it that are not like any other generic logic simulators. Generic logic simulators are the most popular ones because of their modular systems. Beginners will understand the concept of the logic gates much more easily when they see the logic gates with the symbols and highlighted connections. And the experienced users can do their complex circuits for simulating and testing easily too. But when your circuit occupies a proportional space to its functionalities, then you need to take this into an account in your designs too. Reasonable rules sometimes push you to make many compact and efficient circuits. At the 2013 TED conference, artist Phil Hansen made several remarks concerning the value of the limitations. Among them, he said, "We need to first be limited in order to become limitless. And if you treat the problems as possibilities, life will start to dance with you in the most amazing ways." So, like every other backend programmer, I try to recreate this Bitmap Logic Simulator program in my way. My most coding knowledge is on Python, so I started to make this project with Python. Python is a very slow language compared to the original code, which is written on Delphi. My initial design works like cellular automata. This approach is very easy to code, especially when the rules are that simple, but computationally much slower. So, I need to make some optimizations to make my old circuits usable in here too. Otherwise, I don't see any reasons to use my program. My first big optimization on this side project is the idea of compiling the circuit before simulating. The idea was, once the program starts, it scans the circuit and locates all the separated wires and the NOT gates that are connected to them. That way, code doesn't need to rescan the circuit every time the simulation updates. Instead, it will know all the connections and calculate all the wire states by that. And another function updates displayed wires color by looking at a list of ones and zeros that contains wire states. That drastically increased the speed of our simulator. But I thought it would still be improvable. While I was still thinking of ways to optimize the program, I come across with another simulator on Steam called Virtual Circuit Board from Reverie Foundry. I saw similar approaches like that when I was searching for bitmap logic simulators, but this was a very refined form of all I've seen. In the virtual circuit board, you have input, output, and logic pixels. Input pixels transfer the wire states into the logic pixels, and the output pixels takes the result of the logic pixels and change the adjacent wire states. In that way, you can have much more complex designs in much more compact space. I really like the idea of one pixel logic, but I don't want to leave the idea of using only NOT gates. So, I decided to make a similar format that will have only two components, with NOT gate and diode. I wanted to use diodes in my circuits alongside NOT gates because bitmap logic simulator doesn't let you make odd delays. So I started to work on bringing that idea to life. And as you can see, it works flawlessly. I was glad of my job and I thought, okay, I'm done. But something inside me is not done with it, and said to myself, wouldn't it be cool if we can program FPGAs like that? Then I realized it would, yes. And I think it would be too cool if we can make it run on microcontrollers too. And it can be so much cooler that it can turn anything to superconductor state. If it can visualize the simulation while it's running on microcontroller. I think that was the first Eureka moment of this BitBoard project. And that's the end of the video. Thanks for watching. For a while, in the next episodes of the Devlog series, I will still making backlog videos like that. And your comments will be very helpful. If you want to support us right now, you can like the videos, share, and comment whatever you'd like to say to us. See you in the next time.